Okay, good morning. I'm Vittorio Franzese and I'm PhD candidate at Politecnico in Milano. My work is related on autonomous navigation subsystems for interplanetary CubeSats, and what I'm presenting today is the autonomous navigation for the LUMIO CubeSat. So let's start with a brief introduction about LUMIO. LUMIO is the Lunar Meteoroid Impact Observer and is a 12 units CubeSat placed in a hollow orbit at the Earth-Moon LU point. From this orbit, LUMIO will characterize the lunar surface, detecting light flashes due to meteoroid impacts. LUMIO is the winner of a really challenging competition, the LUMIO competition from ESA, that stands for Lunar CubeSats for Exploration, and has been declared feasible by an independent assessment from ESA in February this year. This slide summarizes the orbit of LUMIO. LUMIO will be released in a lunar parking orbit from which it will make its own way to the hollow orbit around the L2 point. In this orbit, LUMIO will stay for 1 year to perform science. So, the main objective from a scientific point of view is to characterize the meteoroid flux in the lunar environment by detecting light flashes on the lunar far side. Moreover, LUMIO will carry on a lot of technology demonstrations. For example, LUMIO will perform autonomous optical navigation, will have an autonomous orbit control, and will use a really innovative optical instrument, the LUMIO-Cam, to detect light flashes on the far side of the Moon. This will be the first CubeSat to autonomously navigate and control its orbit in the lunar environment. The LUMIO Consortium is made up of 5 among companies, industries, and universities, 6, among 5 different countries. So, when a meteoroid is impacting on the Moon, there is the kinetic energy of the meteoroid is split in 4 different categories. There is the formation of a crater, a seismic wave, some particle ejection, and the emission of a flash as a radiation. So the details about the radiation are shown in the slide. The magnitude spans between +5 and +10, and the duration is below 100 milliseconds. This data is needed to model and design the LUMIO-Cam. There are many Earth-based observation programs. One from NASA, one is the NEOTA under ESA contract, and another observatory is in Spain. So why should we observe light flashes from space? Because on ground, as you can see here, if we observe the Moon from ground, then we can only have pulsed observation, as you see in this dashed green line, due to the Earth's rotation, and we can only observe the lunar near side. From space, we can also detect meteoroids impacting on the far side of the Moon, and in this case, we are in the L2 orbit of the Sun-Earth-Moon system. So the LUMIO-Cam is shown, the preliminary design of the LUMIO-Cam is shown in the slide. We'll have a field of view of 6 degrees, resolution 1 megapixel, and a frame per rate seconds of 15. This way we can detect light flashes on the lunar far side. LUMIO will perform autonomous onboard payload data processing so that whenever an image is acquired, it is processed to detect flashes. If a flash is detected, then the image is stored and the region near the flash is stored, otherwise the image is deleted. This is the hollow orbit from the lateral view of LUMIO. From this orbit is a resonance of a factor 2 to 1 with respect to the Sun-Earth-Moon period, so that every synodic period, 2 hollow orbits are done, and in this way operations are steady and it is possible to plan operations. So, since we have a 2 to 1 resonance factor, we will dedicate 1 orbit, the orange one, from the L2 point, 1 orbit to engineering and navigation, and 1 other orbit to science investigation. We will perform science when we see the Moon as dark, from 50% to totally dark to 50% again, and we will perform engineering navigation here in this side when the Moon is lit, as seen from the L2 point, from 50% to 100% lit to 50% again. So Now let's dig into my part in the navigation of LUMIO. Navigation requirements are shown in that table at the top of the slide, where we need from mission analysis constraints and requirements a 3 sigma position of 30 kilometers and a 3 sigma velocity of 50 centimeters per second. When performing station keeping, we also need to increase the accuracy in velocity 24 hours before the station keeping maneuver execution. So let's start with the trade-off. What are the possible navigation techniques for LUMIO? From the ESA SysNova challenge, there was the demand of designing autonomous navigation systems so that the ground-based radiometric tracking is not a viable option for LUMIO. Then we can have the X-ray pulsar navigation, but the development of X-ray for CubeSat is still ongoing, so that optical navigation techniques are most suitable for LUMIO. Among the two, triangulation and full disk navigation, we choose the full disk navigation because it relies on full disk images of the moon that we already have using the LUMIO-Cam for science. So the algorithm is shown in this slide. Whenever an image is acquired, it is processed to detect the edge of the moon. So we have the terminator line and the horizon line. The points belonging to the horizon line are used, and an ellipse is fit to these points, so retrieving the lunar full disk. In this way, we may link the full disk sides in our image to the real moon sides, thus understanding our distance. Since we also know our altitude and the moon position in the frame, we can also have a full position vector. So we developed a simulator at Politecnico di Milano using SPICE, the NASA toolkit, and Array, a free software, a free rendering software. In SPICE, the ephemeris are present, so every position of the celestial objects are made in SPICE, and we can also create some kernels about LUMIO-Cam, the instrument, and the spacecraft. In Array, we can model the moon, and we can set properties so that we go in the rendering engine and we have these nice views of the moon as function of our position during the halo orbit. So this slide shows the static error for LUMIO, so the instantaneous position from one image processing. So again, I want to stress that we have the engineering halo orbit and the scientific halo. This is the range during these orbits, and this plot is the angle between the camera bore site and the sun, so the angle between these two directions. As function of these twos, so when we are far away, the variability in the error as z, so depth, because the error is computed in the camera reference frame, so the z component is the depth. This error increases when we are far away because of the pixel size, which is fixed, so that whenever you have the same error in pixel, you will increase as you increase the range to the observed object. The important thing is that the error is always kept in a, let's say, in a box of 250 kilometers, and this error is used as the worst case for the extended common filter implementation. This animation summarizes the concept. So we have an image during our halo orbit. In this view, you see the halo in this way because this frame is moon-centered and fixed. So we have this image, we process it to retrieve the lunar full disk, and we perform autonomous navigation. This is, again, the static error. So we have an extended common filter implementation, we characterize this error, and we gave to the filter measurements of 3 sigma of error of 240 kilometers. The process of the extended common filter is a high-fidelity model coming from Ultimate, that is the ultra-low trust interplanetary emission analysis tool developed at Politecnico di Milano under ESA contract. The extended common filter settings are shown in this slide. I want to stress that there are different acquisition frequencies, high frequency, medium frequency, and low frequency, to better manage the onboard processing and to achieve the accuracy required during the mission phases. This plot shows the station keeping planning for LUMIO. 3 station keeping maneuvers are planned every engineering orbit, and 24 hours before the station-keeping maneuver execution, we need high accuracy in orbit determination. No station-keeping maneuver is planned during the science orbit, and again, 3 station-keeping maneuvers are planned during the engineering orbit. Whenever we need high accuracy in orbit determination, we use high frequency of acquisition that for us is 1 image processed every minute. Otherwise, we use, let's say, housekeeping data, housekeeping frequency, so medium frequency of 1 image every 10 minutes, and during the science phase, we just use 1 image every hour to prevent the error from going too much. This plot shows the outputs of the extended common filter in terms of 3 sigma position bounds, and you may see that during the engineering halo, the error is always kept inside a box of 30 kilometers, and high orbit determination is achieved whenever needed for station keeping, and during the scientific halo, error is always kept below 50 kilometers per second. So about velocity, we have similar results, meaning that we comply with the requirements. Again, we can have a velocity error kept below 50 centimeters per second during the engineering orbit, and when needed for station keeping, we have a velocity that is kept below 30 centimeters per second. So, we can draw some conclusion. LUMIO is one of the 2 winners of this LUCIO competition, and has been declared feasible by independent assessment in Milano. LUMIO will carry autonomous navigation, optical, for the first time, and CubeSat will carry autonomous navigation, and LUMIO will be the first CubeSat to orbit a halo orbit in the Moon, around the Moon, in the L2 point. So we show also that acceptable performances are possible for CubeSats. So this is all from me. Thank you for your attention.
Thank you very much. Any questions? Oh, sorry. You go first.
Let's go first. Thanks for your talk. I just have a question about the algorithm that you have to put on board. Is it very CPU intensive, or can you optimize it? Maybe.
For sure, it is possible to optimize it, but it is not so heavy because it is not iterative. It's a least square estimation, because when you have this image, you use an edge detection algorithm like Revit, Penny, or other methods to have these first, let's say, points on the image. Then you may refine with some pixel accuracy methods the position, and you can find the position of exact edges of the Moon. Then here you fit an ellipse to these points, and then from here you have a least square estimation that is not iterative. So the computation is not too heavy.
I'm kind of curious about how sensitive to the orbit selection. So let's say you have a little closer orbit or further away, and how this technology would apply in terms of navigation.
In terms of navigation, what is navigation error? In terms of orbit?
Yes.
Okay, as you increase your range for the object, the error increases because you have a fixed size of your pixel, so that if your algorithm makes, for example, 1 pixel of error, this pixel of error, as you increase the range, will increase the depth in your algorithm estimation for the position.
I'm interested in the Kalman filter initialization. I think it's slide 19. Yes, it seems that you take a covariance matrix that is very, very optimistic.
Yes, because we are released from a mother spacecraft in lunar environment, and the mother spacecraft will perform radiometric tracking, so that when we are released, we know our position, because high frequency orbit determination for the mother spacecraft has been planned before we are released, and we assume to have the covariance that the mother spacecraft gives us.
With millimeter accuracy? 10 minus 12.
This is the Q is the process noise. E0 is the initial covariance.
Okay, I'm talking about the process noise. So
Yes,
how do you decide this small process noise?
This is just a value. This is something that we have to work on the process noise. Yes.
Any other questions? No? Okay, well, thank you very much. Thank you.